let's take a look at colligative properties solutions. Okay, colligative properties are physical properties. Okay, so the property of solution that depends on the concentration of a solute, but not identity. The first one is a boiling point elevation. So let's explain this phenomenon in this way. The number of solvent particles of a solution is fewer than the number of pure solvent liquid. Okay, if the solute of the solution is non-volatile, okay, the number of solvent of the solution vaporizes in the gas phase is fewer than the ones in pure solvent. Okay, because the pure solvent has more solvent particles than that in solution. Okay, because solution also has a solute. As a result, the vapor pressure of the solution is lower than that of a pure solvent. Therefore, high temperature is required for vapor pressure reaches the atmosphere pressure. A high temperature is required for more molecules, okay, in solution become gas. So the boiling point is elevated. Okay, this is the boiling point elevation. Next is a freezing point depression. Okay, a solution containing a solute has a lower freezing point than pure solvent. Okay, this is called freezing point depression. This phenomenon can be explained in this way. At a given temperature, intermolecular bond numbers, okay, between solvent molecule in solution is lower than that of pure solvent. So the chemical potential of solution is lower than pure solvent. Okay, take a aqueous solution as an example. Aqueous solution has a lower number of H bond, hydrogen bond than pure water. So the chemical potential is lower in solution than the chemical potential of pure water, meaning that the solution requires less energy, okay, to be in the solid state, or less energy to melt than pure water. So so the melting point or freezing point of solution is lower than that of water. Okay, at 0 degree, okay, this is the freezing point of water. The number of H bond between water molecules in solution is not sufficient for forming ice. Okay, so it's at 0 degree is still in the liquid state. Okay, this is the freezing point depression. And next, let's take a look at a very important concept called osmotic pressure. Osmotic pressure is often used in biology and biochemistry. Okay, before we start to talk about osmotic pressure, let's define the osmosis first. Osmosis is a passage of water or a solvent across a semi-permeable membrane that separates two solutions. Okay, the ions and the large molecules are not able to pass through semi-permeable membrane. Okay, it's osmosis. Okay, what is osmotic pressure? To understand osmotic pressure, we need to do an experiment. Suppose we have two solutions, solution A and solution B, with the same volume but a different concentration of dissolved particles. Okay, the two solutions separated by semi-permeable membrane. Okay, that's the condition for this use permit. Okay, initially the water flow rate from the low concentrated solution to high concentrated solution is bigger than the opposite flow rate from a high concentrated solution to low concentrated solution. Okay, more water flow from low concentrated solution to high concentrated solution. Okay, at the beginning. When the water flow rate from the solution A to solution B and from solution B to solution A becomes same, the high concentrated solution has a larger volume than the low concentrated solution. The pressure caused by the volume difference, okay, between two solutions that balance the concentration effect on water flow rate is called osmotic pressure, right? The greater the concentration difference of dissolved particles between two solutions, the greater the osmotic pressure. Okay, that's the osmotic pressure. Let's take a look at the process one more time here. Okay, at the beginning we have two solutions. Okay, this is the container. Okay, this is semi-permeable membrane. Okay, we have two solutions. Okay, the two solutions have the same volume but different concentration. Okay, this is the A solution, this is the B solution. Okay, let's say B solution has a high concentration and the A solution has a low concentration. Okay, at the beginning they had the same volume, different concentration. So at the beginning the water solvent flow rate, okay, from the low concentration to high concentration is much bigger than the opposite. Okay, opposite from the high concentration to low concentration. Okay, so that's at the beginning more water molecules flow from A to B. Okay, eventually the the water molecule flow rate, okay, flow rates from A to B and from B to A become the same. Okay, then like this. We have the semi-permeable membrane. We have A and B. This is a high concentration. This has a low concentration. Okay, then the flow rate from the A to B and the B to A becomes the same. The water flow rate. Okay, when this rate come to the same, then the the water molecules from A to B and the molecule from A, the flow rate will become the same. So then you can see the high concentrated solution have the high volume. And the low concentration volume, because solution volume become smaller because more water come to the high concentrated solution. Okay, and at this case, this is the high concentrated solution, little bit diluted, and this concentrated, but this still has some difference concentration difference between two solutions. Okay, this difference. Okay, the difference between two volumes. Okay, when the two flow rate become the same, this difference, this is because it's called osmotic pressure. Okay, this is okay. This volume difference. Okay, is balanced. The difference of concentration. This is the osmotic pressure, right?